Look at the sheer scale of this bridge under construction. Beyond the weight of the traffic crossing them, these massive components must fight against their own gravity. At this scale, the weight of the material itself is enough to stretch and deform the very structure it is meant to support. To understand how this happens, we have to look inside the material. Gravity generates internal stress, a reaction occurring at the molecular level. Neighboring particles pull and push against each other, exerting the internal force necessary to maintain their shape and prevent the structure from tearing apart. This graphic highlights our baseline equation for calculating that stretch in a simple, uniform bar under tension, derived from Hooke's law. Let's break down the variables shown here. Delta represents the total elongation. To find it, we multiply the external pull, P, by the original length of the bar, L. Then we divide that by the cross-sectional area, A, multiplied by E, the material's Young's modulus. Before we can accurately calculate the complex stretching of suspension cables or towering skyscrapers, we first need to master how this simple baseline formula reacts when the load is distributed throughout the material's mass. Imagine a single uniform bar suspended vertically from a ceiling. If we want to find out how much this stretches under its own weight, we have to look at the load distribution. A tiny slice at the very bottom of the bar has zero material hanging below it. This means it carries practically zero weight and experiences almost no internal stress. By contrast, a slice at the very top must hold up the entire solid weight of the material hanging beneath it. This section is under the maximum possible stress for the structure. Because the weight adds up as you move from the bottom to the top, the internal force increases linearly. We are moving from zero load at the tip to the full weight of the bar at the support, meaning the weight isn't a static point, but a continuously changing value. To find the total elongation, we have to account for the average effect of this distributed load. Through integration, we find that the standard formula changes. We add a factor of 2 to the denominator, effectively cutting the expected elongation in half. This math reflects the reality of the distribution. Since the internal stress averages out between the zero load bottom and the full load top, the resulting material deformation is exactly half of what it would be if the total weight were concentrated at the very end. This diagram introduces a more complex scenario, a composite or stepped bar. This structure consists of multiple segments, each potentially having its own length, area, and material properties. To find the total stretch for this system, we use the rule of superposition. We must isolate each individual segment, find its specific deformation, and then sum those values together. Isolating these segments requires drawing free body diagrams. By making an imaginary cut through each section, we can solve for the internal resisting forces, labeled here as N1, N2, and N3, that keep each segment in equilibrium. Let's apply this. Consider a two-segment stepped bar. It is being pulled by an external load P'd at the bottom, while also stretching under the distributed self-weight of its own material. Take a moment and pause the video here. Draw the free body diagram for that thick top segment and determine the equation for its total internal force. Engineering structures are simply collections of these individual segments. Mastering the imaginary cut allows us to track the forces in even the most complex designs. Here's the solution. That top segment is supporting three distinct loads: the external pull at the bottom, the total weight of the thinner segment hanging below it, and its own distributed self-weight. Once you identify these forces, you can calculate the total elongation by combining your results from the point load and self-weight formulas. This cheat sheet summarizes our rules. We have the standard formula for point loads, the half rule for self-weight, and the summation rule for composite segments. When you calculate these, meticulous organization is key. You must precisely match the area and material stiffness of each segment to the specific forces acting upon it to avoid critical errors in your final total. Whether a structure is stretching under tension or squeezing under compression, ensuring its survival comes down to accurately tracking those internal resisting forces, piece by piece.